In this module, I'll show you how to solve a problem involving convection in a pipe using ANSYS Fluent. And to show you what the problem is, let me go to my slide. We are given a circular pipe of constant cross-section, and we have uniform velocity coming in. And there are two sections to the pipe. The first section of length L1 is not heated. The second section of length L2 is heated with a constant heat flux QS double prime. And we are given the pipe dimensions, we are given the constant heat flux that's being added, we are given the material properties, which we'll assume are constant. Now, what the flow is going to do in the pipe determines on what the Reynolds number is, and the Reynolds number we'll pick to be 800. And the Reynolds number is defined this way, and the length scale that we use as per convention is the diameter of the pipe, and the velocity scale is the average velocity. And we'll assume that the density is constant, so the average velocity along the pipe has to be constant for mass conservation. So with our given parameters, it turns out we have to pick the average velocity to be 0.1 meters per second to get a Reynolds number of 800. And so if we set the inlet velocity, the constant inlet velocity, to be 0.1 meters per second, that means the average velocity there is 0.1 meters per second, and we will get our desired Reynolds number. So if you want to do a simulation at a different Reynolds number, you can just adjust the velocity coming in. And we will determine, among other things, the temperature variation at the center line and wall. So the center line is like the axis of the pipe, and then you have the wall. We'll determine the mixed mean temperature and the Nusselt number variation, and we'll also determine the fanning friction factor variation along the pipe wall. And I'll get into the definitions of these quantities when we actually calculate them. And so before getting into the ANSYS black box, let's think about what's inside the ANSYS black box as we solve our convection in a pipe problem. Now we'll give it user inputs and turn the crank and get our color pictures and other results, the usual black box framework that I've used in other modules. So you might be familiar with this. And so depending, based on the user inputs, ANSYS figures out what's the mathematical model we want to solve. And that mathematical model is constructed from a physical problem based on some physical principles and assumptions. So the first thing before getting into the black box is to think about what is the mathematical model. So that's the first thing I'll do. And then we will get the ANSYS Fluent solver to solve that mathematical model numerically. It turns out using the finite volume method, and it'll get velocity, pressure, and temperature at selected points. So we need to think about what the selected points are, what are the velocity components to be calculated, and also what are the errors introduced by the numerical solution procedure and how we can minimize that. So that's the second thing we'll do. And then once we have those velocity, pressure, temperature at selected points, we'll do the post-processing that we'll do in ANSYS. And the third thing I'd like to do is do some hand calculations or indicate some hand calculations that you can do of expected results. And so that's a third thing we'll do. Now in this case, we don't have experimental data, so I won't be looking at that. So before we get into ANSYS, let's first think about what is the mathematical model to be solved. And that mathematical model consists of governing equations and boundary conditions. That's coming up next.